Okay, so get started for today. Okay, very good. We have the video. Okay. Hopefully the video is good enough. All right, so we are talking about interference, continuing to talk about interference. And I just wanted to remind you, in the last class, we introduced the Young's double slit, where I told you that this was an example of a type of wavefront splitting interferometer. And that's because in the Young's double slit, as you know, the two slits sample two parts of the same wavefront. And that one wavefront is created, as Thomas Young did at least in the beginning, was created by simply using a small pinhole that creates a spatially coherent source, because that was the difficult part back then, to figure that out, how to do that without a laser. We discussed this fairly extensively in the last class. I'll come back to one or two aspects of it today as well. So, and again, I'm just going through, we derived the spacing between the fringes, we derived what are the conditions for the fringe maxima, and we pointed out the irradiance distribution just follows a standard interference distribution, except with delta, the phase difference now replaced by the expression for the path length difference here, 2 pi over lambda times the path length difference. Okay, why not? Let's see. I don't know if anybody had a chance to look at this. Doesn't seem like God. What is it? There's something. Sorry,
Element.
Light is brightness, I guess.
We have auras,
We all have auras.
which are light.
Yes, they are. It lights up the room. It makes it not dark.
What's the difference between blue light and red light? The color.
It goes in your eyes and then you see stuff.
We range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, it would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s,
How many have seen this very
he proposed
fascinating
that light was a stream of
episode?
particles or
Some of you.
corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today, Thomas Young's double slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803. I brought into the sunbeam a slip of card, but 1/30th of an inch in breadth, and observed its shadow, either on the wall or on other cards held at different distances. Besides the fringes of colors on each side of the shadow itself was divided by similar parallel fringes of slot. This is an experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight. I was thinking about doing it in a box, like a fridge box.
You can take it out on the street.
Taking it out on the street. Could I possibly interview you guys for about a minute? We're doing a science experiment. What I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now, before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom?
The obvious thing you think you're going to see is you're going to see two lines.
Two lines on the bottom of the box.
Two bright bands.
Two little lines. Yeah, I think it'll be one line instead of two.
I can expect it to all most of it up.
That can be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, the colours.
There, have a look. You expected to see kind of one line. Is that what you see?
No,
I see dots.
How many?
it's one circle.
Oh, there's one in the middle strongest, two either side.
The two on the outside are multicolored. One in the middle is just white.
It's kind of a rainbow.
The rainbow colour as well.
Quite a few colours, so lots of little dots.
There are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading. That's that one.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
Two slits.
two slits. Incredible.
But all we're doing is we're putting a light through two very narrow slits side by side. How does this make any sense?
There's some kind of principle involved that the average person is not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up.
Okay, that's a nice video. Search for it. You'll find it, and see the rest of it, which is pretty straightforward for us to understand. Hopefully, by this point in your physics of this course, fairly understandable. But now let's talk a little bit about some of the things that the people saw there. So one thing you noticed was that it was like little dots, right? Not lines that you were seeing perhaps in the pictures that I had shown you earlier. And also the other thing you noticed was there was the colors that were there in that video. Anybody have any thoughts on what the dots are coming from and what the colors are coming from? And the colors, I think you know, but and the pattern of colors that you might expect. What would you expect to see in the color pattern that you observe in that video? What should be the spread of the colors? Should it go starting from the center? Should it be blue to red or red to blue? What do you think? Yes. Blue first and then to red. Yeah, very good. Everybody understand why? Not. Feel free to say no. Talk.
Can you explain?
Yeah, very good. So what is happening is that we have interference, right? And the interference is being caused by whenever there is a wavelength that is satisfying the path length difference. So when R1 minus R2 equals lambda, 2 lambda, 3 lambda, etc., you're going to get bright fringes, right? We agree with that? Yes? So now, if you have blue wave light, is it a shorter wavelength than red or a longer wavelength? Short, exactly. And as we go, let's say we fix our position of observation of approximately, in this, say, one angle or something. Then if you have a certain wavelength lambda, and lambda is longer, then you can see that the angle has to shift a little bit more to make it match the path length for that wave. So red, which is a longer wavelength, needs to be out a little bit further so that the path length difference will match that wavelength to give you the bright fringe. Whereas blue, which is a shorter wavelength, the path length difference can be a little bit less on the order of a wavelength, again, equal to 1 lambda for it to match that way. So blue will be shifted in a little bit towards the center, red will be further out. Does that make sense?
10%.
Okay. How about more mathematically or more visually? Which would you prefer?
Yeah, visual.
Visually. Okay. Well, again, it's as I move out to a certain angle, right? Then what is the path length difference governed by? By the angle, basically.
Are you saying that I don't know what is wrong. So
Bigger piece of time. So we have the two slits here. I'm observing over here, point B. Okay. So my angle of viewing from the center, right? Is theta. Right? And then I have the wave from this slit and the wave from that slit. So when the path length difference, which is this section over here, this is the path length difference between the two waves. How many multiples of lambda can I fit in here? Right? When that's equal to an integer multiple, one wavelength extra over here, you get constructive interference. If it is half a wavelength, you get destructive interference in this little section over here. So if the wavelength is short, blue, then you don't need to go as far out because this you can fit that blue wavelength lambda over full 1 lambda, even though the angle isn't as high. But as I go further out, I need to make the angle. I need a longer wavelength to fit that that distance. Does that make sense?
yes.
Okay, very good. Okay, and I just wanted to go through also phasor diagrams for Young's double slit. Okay, so by the way, we'll come back to the question of why they were seeing the little dots in a minute. But because I want to also go through the math of this in a way that's maybe more visual than the formula. So the formula we derived for the wavelength, but now we're going to use the phasor description. So again, remember we are taking a reference wavelet. Imagine there was no double slit and it was just a single wave coming off in this direction. That would be our reference wave. And then the wavelet 2 and the wavelet 1. And you can see wavelet 1, which is from the second slit, which is down there, is going to lag behind a little because it has extra path to go through. And the first one, which has shorter path to go through, will be ahead by a little bit. Okay. So the phase difference, the total phase difference between wavelet 2 and wavelet 1 is delta 2. We're labeling the 2 subscript for 2 slits. Later on, we'll see n slit interference as well. But for 2 slit interference, we call that delta 2. The total path length difference is delta 2, and the difference from the central wavelet, which is just for reference, we could omit it completely because all we really care about is the interference between the two phasors, between wavelet 1 and wavelet 2. So in principle, we could omit the reference phasor. So if you want, you can ignore it. But the point is that when we draw the two phasors, the E01 and E01 from the slit 1 and slit 2, they both line up when the phase difference is 0. Okay, so imagine now, when is the phase difference 0? Well, delta 2 equals 2 pi over lambda a sine theta, which a is fixed, right? It's this it's the separation between the slit. So when theta equals 0, meaning I'm looking straight in the forward direction. At the center of the screen, I'm looking in the forward direction, right at the center of the screen. That's where I will get 0 path length difference. Delta will be 0. So E01 and E01 will add up. So the total phasor will be 2 E01. And remember, the intensity is the norm of the phasor square. We introduced that a couple of lectures ago. So the norm of this phasor squared will be 4 E01 squared, which is 4 times the intensity of any one beam by itself. Okay, so that's a bright fringe. So if I go off a little bit in angle, such that delta 2 over 2 is equal to pi over 4, which means delta 2 is pi over 2. Okay, so the phase difference between the 1 and 2 slits, the first and the second wave, is now pi over 2, which is what is drawn here. So one, and you can see I'm pointing the first phasor down because that's basically it's lagging behind, right? So it's going downward clockwise, and the second phasor is pointing upward because it's a little bit ahead of the reference phase 0. Okay, so but again, I could also ignore this completely and just draw, the phasor diagram like this, and that would also be accurate. Let me just do it right here. So if this is the first phasor and this is the second phasor. So this is E1 from the first slit and E2 from the second slit. And again, you can see these make a 90-degree angle with respect to each other. That is basically, if I had any arbitrary angle delta, that delta would be over here. So this is delta 2, the phase difference between the two slits is that angle between E1 and E2. In this case, that phase difference is pi over 2. So the phasor diagram looks like this. As you can imagine, the resultant phasor will be square root of 2 times E01 because it's just the sum of these two phases will be just the diagonal of that square. So it's root 2 times E01. So when I square it, I'll get 2 times the intensity from one beam, right? So 2 times E01 squared, which is then just 2 times the intensity from any one slit. So we've gone from 4 times the intensity 4 I naught to 2 times the intensity 2 I naught for a phase difference of pi over 2. And then we can go further when delta over 2 is equal to pi over 2, which means delta equals pi. Okay, then the two phasors point in opposite directions. So now on this diagram, if this is E1, E2 will point in the opposite direction. You can see the sum of those two is going to be 0. You get destructive interference. The total intensity or total field is 0 and total intensity is 0. That's a minimum. So we went from 4 I naught, 2 I naught to 0, and then we can go backward along the same way. 3 pi over 4 will now give me again 2 I naught, but now because the phasors are now pointing in this direction with respect to each other. And then when I go another delta 2 over 2 equals pi, which means delta equals 2 pi. Now the two phasors are again aligned with each other, so they sum up together, but just that they're pointing in the opposite direction from the original phase. So initially they were pointing to the right, now both of them are pointing to the left, and therefore they will add up again together to give you E0. The total intensity is minus 2 times the intensity from one slit. Minus 2 times the electric field from one slit. So the intensity will again be 4 times the intensity from one slit. So this is how, with phasors, we can understand the double slit interference. You may wonder why we need this, because we've already solved the problem using just regular wave addition. But as you'll see, when we do n slits, this starts to become more helpful. The phasor diagrams start to become more helpful to understand the phasor, the physics. Okay, so again, I'm going to remind you, this is from the effects of finite coherence. So whenever the phase difference between two slits is greater than the coherence length, delta LC, and does anyone remember how delta LC was defined? What the coherence length is equal to? What about coherence time? Does anyone remember that? Really? Do you recall discussing it? Or is this gone over the weekend? Vanished. What is the coherence time? And what is the coherence length? Yes, Howard.
I think the coherence time is I don't know if I will remember.
No, that's okay. I welcome any and all answers so we can begin to make some progress.
It sounds like if these two waves are traveling at different speeds, it's how often they make constructive interference or destructive.
Right. So it's whether they can create constructive or destructive interference in a stable way. And you're right, but except the problem is, of course, the two waves do travel at the same speed.
Yeah.
because they're just traveling in air or whatever medium, but they should have the same speed.
But they're
So what is it that causes the interference not to be stable? What might be the reason that they don't have the same, constructive and destructive interference remaining that way? What else could be changing?
the phase.
The phase, excellent. Very good. Exactly. When the phase between the two sources changes randomly, or changes in such a way that we can't predict it, right? Which is completely random, I'm just saying that again. Then that's when you get washing out of the interference fringe. This is a very important phenomenon. You see it in everything from like astrophysics to like quantum physics. So this idea of coherence is very important. So what causes that phase difference not to be stable between the two sources? What were the conditions for interference? How did we derive it? What were the assumptions? Even if you don't remember the math, you should remember the assumptions, the physics assumptions for it. But that's critical. You discuss with your friends. Remember, have some vague approach towards the answers. Okay, I'm going to leave this until I hear an answer. So you'll just have to come up with the answer and figure it out. Because we did talk. Okay, so white light has a coherence length of about 3 wavelengths of the central frequency of 500 nanometers. So that means that we'll only see about 3 fringe maxima on either side. That's because we want the interference pattern. So according to this slide here, which I've discussed in the last class, when the path length difference between the two wave trains is greater than the coherence length, you will not see a stable interference pattern, meaning interference pattern will wash out, you won't see anything. But if it's lesser than the coherence length, then you see an interference pattern. So we want this to be true for white light, which is what was used in that Veritasium video. Then this is about 3 wavelengths, okay, for white light. 3 times the central frequency of 500 nanometers, so about 1.5 microns. So that means, again, since we are doing everything in terms of wavelength, and we just discussed, when one wavelength fits into that path length difference, you're going to get constructive interference. So since the coherence length is on the order of 3 times the wavelength, you'll see about 3 fringe maximum, basically. That's all you can see. That's because after that, the coherence length is lesser than the path length difference. And therefore, you don't see an interference pattern. Okay? So that's why you only see like 2 or 3 dots. Whereas when you did the experiment in the Young's double slit, how many did you see? Oh, you guys didn't do the Young's double slit. I'm sorry. Take it back. Okay. You haven't done it yet with a laser. Although you do see fringes in your Newton ring and the Michelson interferometer, you saw more than that, right? You saw many more fringes over here than 3 with the discharge lamps and so. Okay. Anyway, that's something we can talk about as well.
Yeah, I think we did do the double slit experiment last week.
You did.
Yeah. And this week is like for now.
Oh, right. Yeah, you did it with diffraction under so-called diffraction. Right. So there you did it with the laser, right? Okay. So the laser, you saw a lot of fringes, presumably. Lots, right? It went on and on, basically. So that's the difference. With the laser, the fringe, the coherence length is very long. It can be as long as kilometers, although of course in the lasers you had is probably much less than that, but definitely tens of meters, way more than the length, path length between the 2 slits, for example. Okay. By the way, I just want to point out one more thing, which you will often hear people confuse these phenomena. They'll say, oh yeah, it's the colors. That's diffraction. Or, oh, it's colors, that's refraction. I remember when we did refraction experiments, we did with a prism and we looked at the spreading out of the minimum deviation angle and things like that. So if you do this with, and of course you must all have played with like prisms at some point and seen, that white light in front of a prism, you'll see like colors, right, coming out of it. White, red, green, yellow, and blue. So the difference here is that with a prism, the refractive index is smaller for red than it is for blue, okay? Because n goes as 1 over the wavelength, okay, typically. So because n is smaller, the refractive index is smaller for the red compared to the blue, only a little bit, but that's enough to see the difference. The red will deviate less and the blue will deviate more. So from a prism, if you look at the spread of the colors, you'll see red and then going down to blue, right? Whereas in here, we just talked about in interference, we're seeing blue and then red. So one way to kind of think about, how to differentiate the two is to ask yourself this question, like, is the order of the colors, does it make sense based on the refractive index or based on this interference, which is dependent on the wavelength, directly on the wavelength, rather than 1 over the wavelength like in refraction, okay? So that's another thing that, is helpful to know. Okay, this is just a sketch talking about everything that we've discussed already. I talked a little bit about extended sources in the last class, but this is just to complete the discussion. So we saw that a fully spatially coherent source is like a point source. Point source produces spatially coherent waves, meaning the wavefront, even though there's a temporal coherence, which is limited, meaning that a point here and a point further down the line may not be coherent with each other, may not have the stable phase relationship with each other, okay? The points on the same wavefront, because they're coming from one point source, will have the stable phase relation. This is why Thomas Young's experiment worked, because he put a pinhole first to take the sunlight, and then that spreading light from that pinhole was now spatially coherent, and he could put 2 pinholes to split off the wavefronts and do the interference pattern. So we discussed this last time, and I mentioned that if you have many point sources, then when they add up, they'll interfere with each other in a random destructive or constructive way, and then you'll lose the spatial coherence. So this is just demonstrating that with like different waves. You can see that each of these dashed lines here, this one emanates from a source over here. This dashed line over here emanates from a source over here. And then there's another one over here. There's another one over here. So all of them are basically coming. So there are many sources and they're all spreading out and adding constructively and destructively with each other. So you can start to see that, for example, P1 prime and P2 prime, these are no longer going to have wavefronts that are stable, because now there's a wavefront from source 1 and source 2 and source 3 all adding at the P2 prime relative to P1 prime. The path length difference is going to be different for the sources. And so if it exceeds the coherence length, then immediately you start to get fluctuating interference and fluctuating wavefronts at each of these locations. So no longer we can do this this interference pattern. So that's why extended sources, you don't see the interference very easily unless and until you can like try to just use one point inside the extended source, for example. And there are ways in which we can do that also. So examples of these extended sources, of course, is the discharge lamps, bulbs, and then sunlight, because the sun, the disk of the sun is sufficiently large that it looks extended as far as light is, when the light arrives here on the earth, we can separate out parts of the sun and do the interference, for example, and we'll see that it doesn't maintain a stable, coherent pattern. Whereas if you took a star and you did interference experiments with a star, now that remains coherent because the star is basically like a point source on Earth, as far as Earth is concerned. Okay. By the way, the experiment, the Veritasium YouTube video also showed you this kind of pattern here. You might have noticed that the dots look something like this. This is just a longer exposure of that same pattern. This is the first hint of diffraction within the interference pattern. So these things are the interference patterns. These are like straight line fringes like we've talked about. But superimposed on that, you can see there's like a circular pattern, right? There's like a central bright disk, then a ring, and then another bright disk, and then another ring, and so on. So this is due to diffraction from the apertures, which means essentially the fact that each aperture, the light spreads out, and then when it spreads out, it can also interfere with different parts of the aperture within one aperture. Light from one half of the aperture can interfere destructively or constructively with the other half, or with one quarter and another quarter. We'll go over that in a little bit more detail in the diffraction lecture. Yes.
Yeah. So for is this a diffraction limit for the conventional microscope? So in conventional microscope, there is a diffraction limit.
Yeah.
So when smaller than that, it's the image becomes blurry, and then this is the explanation for that.
Yeah, I'll come to it in when we discuss diffraction. But yes, that's the central reason. Sorry. Okay, I showed this for circular apertures because that Veritasium video that I played for you, they were using little holes, or at least in Young's double slit, they were using holes. Whereas if you use slits, then the pattern will just not be as bright at the end as it is at the center. Now, a slit will also spread out, but it has more. It's essentially infinite in the y direction, so there won't be this ring. It'll just look like the pattern becomes less bright at the end towards the left and the right than at the center. Finally, I want to talk about a little bit more with light. With like lasers, you can do these experiments essentially with hardly any work. Okay, I mean, this is just showing you I can take two independent diode lasers, just run them off of like completely different power supplies and everything. Do interference, I'll see interference fringes. Okay, so even though they look like they should be two independent sources, because they're so coherent, their temporal coherence is so long, and the spatial coherence is so large that essentially they can form interference pattern with another laser. Okay, same thing with like two pulse lasers. I can do it with pulse lasers. I can do it with regular lasers. Anyway, these are just some papers. Feel free to look at them. Because it took, look at this experiments. They're not that long ago. I mean, yes, this is like 30 years ago. But compared to, from when 1801, when the first Thomas Young did his experiment, we didn't try these experiments again with lasers, even though lasers themselves had been around for like 25 years by this point. And these papers are quite easy to read, so I encourage you to look at them, at least. And look at how they had to take the data too, right? These are like pictures of the oscilloscope traces. Because they didn't have like computers and digitization. They did have a digital scope, so they recorded it into the scope and then read it out and all that. But this is kind of how the data was presented back then. Okay, so let's do an example. I think this is good to keep ourselves from getting too lost in the theory. So here's a problem. I want you to like talk to your neighbors and try to like solve this problem first. Okay. So I'll just read out the problem. Two antennas are operating at a frequency of 12 gigahertz, okay, separated by a distance of 10 centimeters. So that's the separation between the sources. An RF detector is initially at the midpoint of the line joining the two antennas. And you get a maximum signal, meaning you get constructive interference. Okay. Hopefully it's clear this is an interference problem. There are two antennas. Okay. Now we move this detector, keeping that same central point in between, but moving it 100 meters out. Okay, so I mean, I can draw the diagram if it will help you, since we don't need to waste as much time on drawing it. Although, of course, if it's an exam problem, you'll have to draw this diagram. Okay. Using to mute. Okay, well, I don't know why it won't mute. This display is having some problem. Okay, well, I'm sorry, but you just gotta deal with that. Okay, this is antenna 1. This is antenna 2. These are the two sources. I can label them S1 and S2. Okay. Initially, the detector is at the halfway point, okay, deep. And I'll put the numbers up again. I forget what it is. 100 meters? So
10 centimeters apart.
Let me look again. Oh, yeah, the antennas are 10 centimeters. Sorry. And initially at the halfway point, they are you're getting a maximum signal. Now I move it 100 meters. And I put, imagine there's effectively a screen at that distance. So now I put the detector over here. Will I get a high or low signal here first? How do I find that out? Yes, anyone? Yes. High signal, why is that? Exactly, very good. So there's no path length difference. Everybody understand that, right? This is exactly still equidistant, even though I moved it 100 meters out. The distance from S1 to that point, let's call that point P, P1, is still going to be the same as from S2 to P1. Okay, now I move this 100 in a line perpendicular to this original position while staying in the same distance. So approximately still 100 meters, but I'm moving, let's say, the detector, walking the detector up and down this sort of plane, right? So how far do I have to go? What is the distance over here, H, before I get nearly the same signal strength, meaning again, I get a maximum. How do I find this out? What is H? Okay, you can talk to your colleagues, friends, and think about how you might find out this distance. By the way, the frequency of the sources is 12 gigahertz. You're too far from anywhere. No.
Yeah, kind of.
So, do it.
Remember the equation.
Yeah.
You don't remember the equation, how can you derive it? You actually had to remember it. No, you have to think. If you can't derive, you think, right? Or if you can't remember, you think.
M-land.
There is an M-land.
Yeah,
I encourage cross,
and there's something with this.
disciplinary work.
Yeah. But what if sine theta is times something?
Sin theta times something. What is that something?
This slit width or distance.
Right?
Oh, that's
Very good.
10
10 centimeters. So if A is 10 centimeters, the separation between the slits, then somebody said A sine theta equals M lambda. Very good. Right? That is the equation that you were asking for. So that tells us the thetas at which constructive interference will take place. Clearly, theta equal to 0 is the center of the screen, which we already agreed has constructive interference. By the way, why was it so important to know that you had constructive interference here first, before I told you that it's also, before we had to guess it was constructive interference there? For example, could I make this destructive interference over here? Between at that midpoint? Yes, I could, yes?
That now the sources are in phase with each other.
Very good, exactly. So because they're RF sources, it's kind of easy to synchronize. In fact, this is done in all the telescopes, the radio telescopes. they have like synchronization between the radio telescopes and so on. That's a separate topic, but anyway. So you can synchronize the sources and you can drive them to be in phase with each other. So anyway, coming back to the main point now, if you introduce a phase shift of pi here, then you get destructive interference in the middle, and that would also remain over here. Okay, now we have theta. So can I now get H from knowing theta, where I get the first maximum, theta 1, or that's the first maximum, and that's the first interference fringe maximum on the side. Knowing theta, what is H? Do I need formula or can I figure it out? Jack.
We use an approximation if it's too far.
Exactly. We have to use an approximation all the time because we are always in the far field. Remember when we talked about general interference considerations, we are generally with interference looking at far field things. Okay. Although in today's labs, you may be looking at near field stuff, but at least for most of the theory work in the interference and diffraction chapters, until we get to Fresnel diffraction, which is today's lab, we'll be mostly working in the far field. So sine theta is approximately tan theta, and is of course approximately theta. Okay. So tan theta, right? Can I get that from the triangle? Yes. 1, 3. You can get it.
Yeah. So for the far field, so this corresponds to the small angle.
Yeah, small angle. Very good.
Okay.
Exactly. Right. So from here, tan theta is equal to what in terms of h, and if I call this distance L equals 100 meters. So tan theta equals in terms of h and L. Or somebody gets it. Yeah. H on L. Very good. Okay, so we have everything we need. Let's plug back. Oh, well, wait a minute. What about lambda? And the frequency? What is the relationship between lambda and the frequency? Yes, everybody had too much to eat for lunch. Lambda and frequency. Yes, definitely. V, what? Speed V, yes, very good. Lambda times. Very exactly. All right, so we have everything we need. Now I'll just plug it in. We'll get the answer. Okay. So that was our example. Oh, wow. I spent most of the class on that. Okay, let's try to wind up Young's double slit stuff today. So we can move on to the other interference phenomena. Oh, well, I should talk about another experiment that you get to do in this lab, also in 1426, which is single photon interference. Okay, so you're going to do an experiment if you choose to do this special project where we've been talking about using extended sources, light bulbs, etc. But now you can do it with a single photon. Okay, so I won't say more about that, but this is kind of the pattern you'll see when you count the photons. You'll get more photons at the fringe maxima and less photons at the fringe minima, even though at any given time there's only one photon in your set. Okay. Feynman called this. I was going to ask this as a quiz. Shit. I already said who this that said this, but I can't overemphasize because even if you don't trust me, you trust Feynman, I think. And he called this the central mystery, which is absolutely impossible to explain in any classical way. It is the heart of quantum mechanics. Okay? This idea of interference between objects, between particles, for example. Okay? And of course, since many of you didn't come to my lecture at SPS, you get to still experience a little bit of the magic of my talk at SPS, which is, I can get this to play. Right. You get what do you get? What do you get? Trust them, right? Teen Titans. Right. That's right. Oh. Okay. That is, I saw that with my kids one day on watching Sunday morning cartoons, and I show it every time. It's just a text. Okay, so what they were talking about is this famous experiment in the 1990s. It's the first time it was done with electrons, which demonstrated that this wave property, not only for photons, but also for electrons. And what they observe, as you can see, is when they fire the electrons in, they only observe like one detection event at a time. So you can see after a few minutes of running the experiment, there's a dot here representing one electron, another dot here representing one electron. At first, it seems like they're just appearing randomly across the screen. You can't predict in any given run of the experiment, you can't predict where the electron is going to end up. Okay, you don't know where it is. But as you shoot more and more of them, the probability distribution follows our cosine squared function, the irradiance distribution that we have shown in this class as well. So there is interference of the electrons, but that only shows up in probabilistic way that even though we can't predict which slit the electron is going to go through or where it's going to land on the screen, over time, as we accumulate statistics, we can predict the probability distribution of the electrons. This, of course, is the heart of quantum mechanics as well. And this is the interference not just of like electrons. It has been, experiments have been extended to things like molecules and so on, up to, this is actually old. I should update this. But this is like buckyballs. If anybody knows what buckyballs are, have you heard of buckyballs? Okay, these are macromolecules of like 60 carbon atoms in like a cage-like structure. It won a Nobel Prize, by the way. The person who discovered these buckyball type molecules won a Nobel Prize. And now, this is an experiment where they did the same experiments with buckyballs. So these are like pretty big on the scale of an atom. These are fairly large atoms or molecules. And that was seen. And now it's been extended to much larger molecules. Okay, I'm almost done. I just want to say one more thing because I want to conclude the Young's double slit stuff. So, of course, Young's double slit, we kind of require the ability to make the slits. Remember, the separation between our fringes is governed by A sine theta, right? It's like A sine theta equals M lambda. So sine theta is roughly on the order of 1 at most. So A roughly has to be equal to lambda for the interference. So, for example, the spacing between the fringes is like lambda in the path length, which is governed by this A, the slit separation. So A has to be on the order of lambda. It can't be like millions of times lambda, okay? So that's why, for example, to observe the interference, you put the two slits close together, okay? Well, there are many wavelengths, for example, gamma rays or X-rays and so on, where it's difficult to build slits or like sources such that the two are separated only by a wavelength or half a wavelength or whatever, tens of wavelength even, okay? So for example, this is an experiment, I think this is done with like 190 nanometer, or maybe it's 90 nanometer radiation, which is definitely in the X-ray regime. And so these are the interference pattern that you're seeing, and this is done using something called the Fresnel double mirror configuration. Because even though it might be hard to create sources or to separate the slits, etc., by like that small an amount on the order of like tens of nanometer, it's fairly easy to make mirrors out of materials. So, for example, many metals are still very good reflectors, even out to like large wavelengths. Crystals, it turns out, are good reflectors for like X-rays and things like that. So by using crystals or by other metals and so on, we can make this double mirror configuration. You notice that there's an angle now between the two mirrors, and you see that the reflection from one mirror, if you trace it back, that's the virtual source, basically, a virtual object, coming back to our geometrical optics picture. And then this is another virtual object from the reflection of this mirror, okay? And we know how to predict where those two sources will be just by using ray tracing or other geometrical optics argument. And now these two sources, S1 and S2, their separation A can be again controlled effectively by this angle 2 theta, or by angle theta, basically, okay? And you can work out the geometry of this. I won't go into that, but it then allows us to again carry out fringe interference experiments. And this is another, actually the electron interference experiment that I was showing you was actually not done with two slits, but was done with something called a Fresnel biprism, which is shown over here. And this same idea, because with electrons, it's easy to sort of control electron paths using things like voltage plates and like inductors and so on, right? You can just like, it's a charge, so you can control the charge. And what they found is, for example, this is done in the optical domain, but the same idea applies with the electron waves. So here in the optical domain, you have a prism, and the angle of this prism alpha, this opening angle as we call it, you can see you have a single source of electron, which is an electron gun. And then as it undergoes refraction, this creates a virtual object here. As this undergoes refraction, that creates another virtual object here. The separation A over here is again governed by this opening angle alpha. So by like changing that opening angle, we can basically control the separation A. And again, we can make that such that you get interference. This was, I think, this interference pattern was done with, I think, X-rays. Actually, it was the same electron experiment, except they shot like a huge number of electrons through right away. So instead of observing them one electron at a time, and then you see these perfect, kind of standard white straight line fringes that you would expect from a Young's double slit. Okay, that concludes. One more wavelength splitting wavefront splitting infrared, Lloyd's mirror. This is also a very nice one. Actually, this, I won't go into the details. You can look this up. I'll put the slide up. If you have any questions, you can come and ask me. But the one thing I do want to point out is this actually can occur naturally. So, for example, the ionosphere serves as a sort of a mirror for like radio waves. So you can observe interference patterns of the radio waves bouncing off the ionosphere and creating, again, the same idea. You have the radio waves or any other wave bouncing off a mirror at glancing incidence. Remember, at glancing incidence, we discussed almost every mirror, every surface, almost any surface at glancing incidence becomes a mirror. Okay, so you could even have this, this table at glancing incidence sort of looks reflected, right? So that's the same idea. So like lakes can become like mirrors at like glancing incidence, and then there'll be this virtual source which is down here. And we have seen from Fresnel's coefficients that at glancing incidence, the reflection coefficient is exactly -1 almost. So which means that there's a phase difference of pi, which shows up here in the phase difference. So an extra phase difference that you have to add in. And then everything else is just K times R1 minus R2, just like before. Okay, so this has been seen with crystals, with microwaves using wire grids, and then with radio waves, with lakes, Earth's ionosphere, etc. Okay, that concludes wavefront splitting interferometers. The next class, I'll do amplitude splitting interferometers. Thanks.